students, today we are going to start the unit 4, that is monostable and stable multivibrator. So in the last unit we discussed about what is meant by multivibrator and what are the types of the multivibrator, and in that we discussed about the bistable multivibrator. So what is the multivibrator? Simply we can say that multivibrator nothing but oscillator with amplifier with a feedback connection, or it can be known as a free running oscillator. So without any input signal, it produces the output and it produces the oscillations for various frequencies. So simply we can say that a multivibrator which can produce oscillations for various frequencies. So that is about the multivibrator, and multivibrator can be divided into 3 types based upon the states. And they can be called as what is the state? Simply we have 2 types of the states. And what is the quasi-stable state? So coming for the stable state, we can say that with an external triggering pulse only, it can change the state of the signal. Nothing but we can change the state of the signal. So this particular state is known as a stable state. And coming for the quasi-stable state, without any external triggering pulse, it moves to the previous state after predetermined time. So this is known as quasi-stable state, and generally based upon this, a multivibrator can be divided into 3 types, that is bistable, monostable and stable. So in the last unit we discussed about the bistable multivibrator, and in this unit we discussed about the remaining 2, that is what is the monostable multivibrator and what is the stable multivibrator we have to discuss in this class. So first one, that is what is the monostable multivibrator. So first we discuss about monostable. As a name itself, monostable, nothing but it consists. So monostable multivibrator consisting of single stable state and single quasi-stable state. And quasi-stable state. Simply monostable multivibrator having simple one stable state and one quasi-stable state. As we know that in stable state we use that is resistive coupling, and coming for the quasi-stable state we use the capacitive coupling. So the coupling is also different, and here the monostable multivibrator we use both types of coupling. Why? Because it consisting of one stable state and one quasi-stable state. So simply coming for the definition, a multivibrator which is having one stable state and one temporary, that is a temporary state, nothing but quasi-stable state, and level of transition depends upon external triggering pulse. So let us discuss that. My example will be like this. Obviously the multivibrator consisting of the transistor. So let us example, that is Q1 is off condition in the initial state and Q2 is in on condition. So when I am giving an external triggering pulse to the circuit, so that we can change this particular state. So nothing but changing from stable state to quasi-stable state. So simply we have to say that Q1 is off and Q2 is on. So simply in this stage it goes to the quasi-stable state. After some time it moves to the previous state without any triggering pulse. So coming for the stable state, we apply a triggering pulse. So changing from stable state to another state, we obviously applying that is triggering pulses. But coming for this transition of quasi-stable state to normal state, we don't apply any triggering pulse. After predetermined time, it moves to the previous state. Why? Because here we use the capacitive coupling. So that is the major thing about this one. And next one is so this is about the definition of the monostable multivibrator, and simply the monostable multivibrator, the another name of this monostable multivibrator is known as one shot or single shot, and it can be also it is also known as a univibrator. So why? Because it consisting of single stable state. So that is, it is also known as a univibrator, and it can be like this. This can be used as a pulse generation. So major application of this one is used in the delay circuit. In the delay circuit we use the pulse. So generation of pulses, we go for these types of monostable multivibrator. Simply monostable multivibrator, it converts this type of signal, nothing but pulses of signal to the square waveform. So simply this is about the monostable multivibrator. It is consisting of single stable state and single quasi stable state. After that it can be also known as one shot or single shot. So the another name of this monostable multivibrator is one shot or single shot, and at the same time it can be also known as uni vibrator. So uni nothing but single vibrator or bistable simply multivibrator, uni vibrator. So the another name of this monostable multivibrator. And next one, and types of monostable multivibrator. So as like the bistable multivibrator, monostable multivibrator is also divided into two types, that is collector coupled monostable multivibrator and emitter coupled monostable multivibrator. So simply coupling nothing but the output of one transistor is connected as input of another transistor, as we know that condition. And as like that bistable, we also splitted the monostable in two parts, that is collector coupled and emitter coupled. In the collector coupled, we use that collector, that is output of this one is connected to the base, and in emitter coupled we use the emitter connection. So that is both the emitters will be connected. In the collector coupling, both the collector terminals will be connected. So in this session we discuss about the collector coupled monostable multivibrator and what is the operation of this particular one. At the output waveforms, very important, and we discuss about these things in this class. At the same time, what is the pulse width of the monostable multivibrator we have to discuss. Simply we have to say that so this is the circuit diagram for the monostable multivibrator. Here we use the two transistors. Obviously in the collector coupling or any multivibrator we use the two transistors. So here we use that as usual connections will be like this, Q1 and both the emitter Q2. Here both the emitter terminals will be connected to the ground. At the same time, the collector terminals will be connected to the VCC through resistor RC, and this one will be RC, and both are connected to the VCC. And here we use a coupling element, and which coupling we have to use? For stable state we use the resistive coupling, and for quasi stable state we use the capacitive coupling. So monostable multivibrator having both state, that is it consisting of stable state and quasi stable state. Simply it will be like this, that is capacitive coupling I am using here. So nothing but this one is a quasi stable state, and resistive coupling I am using here. And in case of resistive coupling, obviously we have to connect the biasing. So that is a major thing. So in case of using any resistive coupling, obviously we have to apply the biasing voltage. So that's why in place of resistive coupling, the another terminal will be connected to the minus VBB, that is biasing will be applied to this, and this one will be R2. Here this one is a biasing resistor, and in place of capacitive coupling we connect a resistor. Why? Because so without any resistor the charging and discharging will be not performed in correct manner in the capacitive. That's why for the charging and discharging part we have to connect a resistor to the VCC for capacitive charging and discharging condition. So this is a circuit diagram of the monostable multivibrator. So that is collector coupled monostable multivibrator. Simply we use the stable state as well as quasi stable state. In the stable state we have to connect, that is resistive coupling we use. In the quasi stable state we use the capacitive coupling, and in resistive coupling side we use that is minus VBB, that is a biasing voltage, and in the capacitive coupling we apply the resistor, that is for charging and discharging we have to connect a resistor path here. Operation, what happens and what is the operation of this one? So let us assume like that. So in the initial stage we assume that one transistor Q1 is in off condition and Q2 is in on condition. So this voltage is known as VA and this one one will be VB and this one will be VC and this one will be VB. We have to take like this. So VA, VB, VC and VB. So let us example that is transistor, assume that the transistor Q1 is in off condition and transistor Q2 is in on condition and nothing but it goes to the saturation region. And what is a VA, VB, VC and VD? So when transistor Q1 becomes off condition, obviously the VA voltage will be negative. That is a negative. We apply the negative biasing here. That's why the VA voltage will be negative. And what is the VB? So when transistor Q2 goes to on condition, that is VB nothing but VBE saturation. Why? Because transistor Q2 is in on condition and this one is VC. VC nothing but when Q1 goes to off condition, what is the VC value? VC nothing but VCC. So that is a principle of transistor. When transistor goes to off condition, the collector voltage VC becomes VCC. That is VC becomes VCC and VD becomes VCE saturation. So this is the conditions. So what happens and what is the condition here? So simply, so this capacitor, so what is the principle of here capacitor used? It is used for charging or discharging purpose. So in this time, the capacitor is connected in between VCC and this terminal, that is a VB. So simply the capacitor starts charging in the manner of like this. So capacitor starts charging in this manner. That is, it starts charging through RC and C1 and this one. Simply the path of charging will be like this. That is when transistor Q1 goes to off condition and Q2 goes to on condition. In this time the capacitor starts charging. The path for this one is RC1 and this one will be VCC and here we use a capacitor. After that it gives to the VB and transistor Q. The charging path will be like this. This one is C1. With an external triggering pulse is applied to this condition. So then only it moves to the next state. That is, we apply a triggering pulse to the circuit. So where we apply triggering pulse to this monostable multivibrator or any multivibrator, simply it is applied in two positions, that is off transistor collector terminal or on transistor base terminal. At which triggering pulses we have to apply? That is, we apply a negative triggering pulse. That's why we have to apply a triggering pulse at the off transistor collector terminal or on transistor base terminal. Here I am applying a triggering pulse at this off transistor collector terminal. Then it gives to the transistor Q1 goes to Q1 goes to off condition and Q2 goes to Q2 goes to off condition and Q1 goes to on condition. Why? Because with an external triggering pulse is applied to this external negative triggering pulse is applied to the transistor Q2 base terminal. Then transistor Q2 becomes off condition. When transistor Q2 goes to off condition, this voltage will be VCC. This voltage is applied to the transistor Q1 base. Then Q1 goes to on condition. So that is stable state to next state transition. But in this time, what happens? What is the condition? We apply a triggering pulse here and what is the condition? Simply, we apply a triggering pulse, then Q1 goes to on condition with an external triggering pulse. So Q1 goes to on condition and Q2 goes to off condition. So this one will be VA and this one will be VB and this one will be VC and VD. In this time, we have to check the VA, VB, VC and VD. So obviously, VA becomes VBE saturation and VB nothing but it is in terms of negative and VC nothing but VCE saturation. Why? Because transistor Q1 is in on condition. So that's why the collector voltage VC nothing but VCE saturation. And what is the VD? VD becomes VCC. Here what is the condition of capacitor and what is the position of this capacitor? The capacitor is connected in between this VCE saturation, that is 0.7 volts, so 0.3 volts and negative. So in the previous time, that is when transistor Q1 in off condition, capacitor is doing charging. But in this time, capacitor starts discharging. So why? Because it is connected in the negative, that is VC SAT and VB, that is negative voltages. Then capacitor starts discharging. So in the previous one, capacitor is doing charging, but in this time the capacitor starts discharging. That is, discharging path will be like this. Simply we can say that discharging path is like this. So the discharging path, for discharging of capacitor, we use this resistor R2 and capacitor and Q1. So again I have to draw this discharging path. Simply the discharging path will be like this. So capacitor C1 and this one will be R1, R2. So I am using R1 only, that is R2. And it gives to this one. And this another terminal will be connected to the, one terminal of capacitor is connected to the VC, another terminal is connected to the VB. VB is obviously connected to the transistor Q2. So generally the discharging path will be this one. So but when the capacitor starts discharging, what is meant by discharging of capacitor? Simply we can say that when the capacitor starts discharging, it releases the voltage, nothing but. So it releases the voltage. When it starts discharging, then the voltage at VB starts increasing. Nothing but one terminal is connected to the VCC, another terminal is connected to the VB. So in this time the capacitor voltage will be, that is the released voltage is applied to the VB, base of transistor Q2. Then the Q2 starts conducting. When it goes to the VB saturation, that is VB goes to the VB saturation, then Q2 becomes on condition without any extra triggering pulse. So this is the operation of the monostable multivibrator. Simply we can say that at initial stage we assume like that one of the transistor is in on condition, another goes to off condition. So that is Q1 is off and Q2 is on. So in this time the capacitor is doing charging, and with an external triggering pulse only we can go to this Q1 is in on condition and Q2 is in off condition. So in this time what happens, in this time the capacitor start discharging. So nothing but this particular stage is known as quasi-stable state. So in this time the capacitor starts discharging. This discharging voltage will be given to this transistor Q2 base terminal. When it reaches the VB saturation voltage, obviously the transistor Q2 will be conducting. So that is a condition of monostable multivibrator. Without an external triggering pulse, it moves to the previous state. So that is the previous state will be Q2 is on and Q1 is off. So that's why we, without any triggering pulse, we go for this state. So this is the operation of the monostable multivibrator. And let us check the waveforms of this monostable multivibrator. So this is very important for this. So we have to consider these waveforms. The first one will be VBE2. So the VBE2 nothing but a transistor Q2 base terminal. So what is the transistor Q2 base terminal and what is the waveforms here? Simply in the initial stage we assume like that Q and Q2 will be on condition. So in this time what is the base VBE value? The VB is equal to obviously VBE saturation up to this position. So with an external triggering pulse only we can change this state, that is we move to the Q1 is in on condition and Q2 becomes off condition. That is Q1 is in on condition and Q2 becomes off condition with an external triggering pulse only. So in this time obviously the voltage will be decreased in the negative direction. So in this time what happens? So Q1 is in on condition and Q2 is off condition. What is the condition of capacitor? Capacitor starts discharging. So that is Q1 goes to on condition and Q2 goes to off condition. The capacitor starts discharging, but when capacitor starts discharging it releases the voltage. So at which position the voltage will be increased, that is in the VB position the voltage will be increased in exponential manner. Simply the capacitor is discharging, so then the VB voltage will be increases exponentially. So it reaches the zero value at t is equal to capital T, that is RC. So but actually it discharges up to the maximum voltage, but so when it reaches the VBE saturation, it goes to, that is a transistor Q1 goes to off condition and Q2 goes to on condition. That is, when the VB voltage is reaches to the VBE saturation, obviously transistor Q2 goes to on condition, and this extra is a point, that is the extra thing is represented with the overshoot. So this one is known as overshoot. In this time we have to measure the VC1 as well as VC2 and VB1 also. So when the capacitor is connected, in this time it gives the slope type of signal. So another terminal of one terminal of capacitor is connected to the VB, another terminal will be connected at the VC. So when the transistor Q1 is in off condition, what is the VC1? That is VCC. When transistor Q1 goes to on condition, it goes to VCE saturation. And when again it moves to the Q1 is off and Q2 is on, but in this time the capacitor is doing nothing but capacitor start discharging. So that's why this slope will be increases in this manner. So there is some discharging. This is due to the capacitor. So at the time, what is the VC2? That is in the initial stage Q1 is off and Q2 is on. When Q2 is in on condition, the voltage will be VCE saturation, and Q2 is on, it goes to VCC, and finally it goes to VCE saturation. So remember this thing, when capacitor is connected in between any terminals, so in these terminals only the slope signal will be different. And the final one, VB1. In the VB1, in the initial stage this signal will be negative, and after Q1 is on condition, it goes to VBE sat, and after that it goes to the stable state. So this one is the waveforms of the monostable multivibrator. So the first one is base VB2 and VC1, that is collector at transistor Q1, and second one is collector at transistor Q2, and third one is base of transistor base of transistor Q. So this is about the collector coupled monostable multivibrator and their circuit and their waveforms. And what is the applications of the monostable multivibrator? Simply, the monostable multivibrator is used like this. That is analog system to control the output signal frequency. So it is used in the analog system. So it is by using this we can control the frequency, and for synchronizing at the same time by using this we can use it at the major application will be pulse generator. So this is known as a pulse generator, and moderate the tunes of different with electronic organs. Nothing but it is used for electronic organs. So this one is the major applications of this monostable multivibrator. And next one is the expression for the pulse width or delay time. So here we have to find the expression for the pulse width or delay time. So simply, we can, that is the base of transistor Q2. So in this time only we have to find the pulse width or so that is a pulse width or time period of the any multivibrator. Simply we have to say that, so that is the VB is at, and in this time the transistor condition, that is Q1 is off condition and Q2 will be on condition. In this time, what is the major, what is the condition? It is in the stable state. After that we move to the, that is Q1 is on condition and Q2 will be off condition. In this time the capacitor starts discharging. When capacitor is going to discharge, in this time this will be like this. This state is known as quasi-stable state. So in this time this particular state is known as quasi-stable state. After that this stage, next stage it goes to the, that is Q1 is off and Q2 is on. Again it moves to the stable state. Simply for finding of pulse width we have to take this quasi-stable state condition. That is Q1 is in on condition and Q2 is in off condition. Obviously capacitor starts discharging. So as we know that what is the mathematical equation of the capacitor, so function, simply we have to say that this one will be VB. So we know that what is the VB? VB is equal to, so simply we have to say that VB is equal to V final minus V initial into e power minus t by RC. So this is the standard equation for capacitor charging or discharging, that is V final minus of V initial into e power minus t by RC. So just to check the condition of what is V final and what is the V initial here. So simply we have to say that what is the initial value. So where it starts discharging, the initial value, discharging, it starts at minus VCC. Simply the discharging value V initial is equal to minus VCC, and what is the V final? Actually it starts charging up to the maximum level. What is the maximum level of this capacitor? That is VCC. So this is the maximum level, but when it reaches the VB sat, Q1 goes to off condition and Q2 goes to on condition. But we have to take that V final value will be obviously V final is equal to VCC. Just substitute these values in this equation and we get the pulse width of this one. Very important, and just check the condition. So just I have to write this. Capacitor C discharging, then VB voltage increases exponentially and it attains the VCC, but at the time of t is equal to T, the transistor Q2 becomes on condition. That is, here we take the ideal condition, that is at t is equal to T, the transistor Q2 goes to on condition. So simply we have to say that, so then VB is equal to V gamma, we have to take it as 0. And then in this time VB is equal to, we have to substitute V final minus V final into e power minus t by RC. As we know that what is the V final value, that is VCC, and what is the V initial value, so that is V initial value is equal to minus VCC. From this we have to solve the what is the VB. So simply what is the VB? That is VB is equal to V final nothing but VCC minus V final minus V initial, that is VCC minus of minus VCC e power minus t by RC. Simply we have to say that is VB is equal to VCC minus of VCC minus of minus, that is 2 VCC e power minus t by RC. As we know that at t is equal to capital T, what is the VB value, which is equal to V gamma? We have to take it as 0. Why? Because in that particular condition V gamma is equal to 0. So just at t is equal to capital to V gamma, which is equal to 0. Just substitute the 0 here, that is VCC minus 2 VCC into e power minus t by RC, and just take this 2 VCC in the left hand side, that is VCC is equal to 2 VCC into e power minus t by RC is equal to VCC, and that one is so what is the e power minus t by RC? VCC by 2 VCC, both will be cancelled, and e power minus t by RC is equal to 1 by 2. And what is the minus t by RC? Simply by applying natural log on both sides, then we get that minus t by RC value, that is minus t by RC is equal to, so simply minus t by RC is equal to ln of 1 by 2. So just substitute the value of ln of 1 by 2. So simply we get that, so minus t by RC is equal to ln of 1 by 2. So that is minus t by RC is equal to minus 0.693. Minus will be cancelled, and t is equal to 0.693 RC. So this is the equation of the pulse width. So final t is equal to 0.693 RC. Just we know the value of resistors and capacitor, then we get the pulse width of this particular monostable multivibrator. So this one is another concept in this unit. And the next one is what is the application and major application of the monostable multivibrator. Simply the monostable multivibrator can voltage to frequency, time converter. So the major application of this monostable multivibrator is simply it can be used like a voltage to time converter. How it can be like this? How it can be performed like this? Simply we have to check the condition. So again the same diagram, but here we have the condition, that is VCC. In place of VCC we have to take the value of V. Simply the value here will be V and the remaining process will be as usual. Why? Because so we have to prove that one, that is the monostable multivibrator is used as voltage to frequency converter. For this we have to add a voltage at that resistor R. Simply the diagram will be like this for this particular operation. Both the emitter terminals will be connected to the ground and resistors RC1 and RC2 which is connected to the VCC, and RC1 and RC2. Here it will be connected to the capacitor and this one is connected to the resistor. Here we connect the resistor actually. Here also we connect a resistor for biasing minus VPV. And this resistor will be generally connected to the VCC, but here I am connecting a resistor with voltage source with. So that is the difference between this previous and this one. So that's why charges are discharging. It is discharging up to V voltage only. So that's why we have to indicate that one V. So this is the diagram for this particular voltage to frequency converter. And in this stage, as like that, the capacitors start discharging. What is the equation of the capacitor discharging? Simply we have to say that the VB is equal to V final minus V final into, V final minus of V final minus V initial into e power minus T by RC. So in that, what is the V initial value? Like that, the V initial will be minus VCC. Why? Because it starts here. So that's why V initial is equal to minus VCC. And what is the V final? The V final will be V volts. So just substitute this value and we get the how it can be performed voltage to frequency conversion. So that is VB is equal to V final minus V final minus V initial into e power minus T by RC. And what is the V final value? V final value will be V minus, and V final will be again V, and V initial will be minus T by RC. And this one will be V of V plus VCC e power minus T by RC. As we know that at T is equal to capital T, at T is equal to capital T, VB will be V gamma which is equal to 0. Just substitute the 0 here. 0 equal to V minus V plus VCC into e power minus T by RC. So then what is the value of V? V is equal to V plus VCC into e power minus T by RC. What is the e power minus T by RC value? E power minus T by RC is equal to V by V plus VCC, and e power minus T by RC value is this one. And what is the e power T by RC? It becomes V plus VCC by V. So simply e power T by RC equal to V plus VCC by V, and VV will be cancelled. It can be write like this, 1 plus VCC by V, and the T by RC becomes ln of 1 plus VCC by V, and T becomes capital T or small t. T is equal to capital T, that's why we have to represent capital T only. That's why in place of small t we have to represent capital T. T is equal, what is the T value? T is equal to ln of 1 plus VCC by V into RC. Simply we have to say that here the VCC value is constant. That is the resistor and capacitor values are the default values. We can't change these one conditions. These are the given data. So with variation of this resistor V only we can change the time. So with variation of this V voltage, we can change this time T. So that's why this circuit is known as voltage to time converter. So that is about the monostable multivibrator and what is the application of this monostable multivibrator. And the next one will be up to this we discuss about what is a monostable multivibrator and what is the major operation of this monostable multivibrator. At the same time, what is the pulse width of the monostable multivibrator and how it can be performed like voltage to time conversion we have to discuss in this class. And the next one will be design of the monostable multivibrator. So, and what is meant by designing? So, in the designing process, so they have to give the voltages and currents and we have to find this resistor, capacitor values. So, simply we have to know that so that is assume the first condition will be they have to give these values VCC and that is current IC2 current they have to give and HFE value if required they have to give the conditions. Obviously they have to give these values. They give the VCC, HFE and RC values they give in this problem. So from this we have to find the what is the RC1 and RC2 and what is the R and R2 we have to find in this designing concept and what is the capacitor value we have to find also. Simply we have to say that the first assumption will be, so the first assumption will be we have to assume like that one of the transistor will be off condition, another one goes to on condition. That is Q1 is an off condition and Q2 is an on condition. Just first condition will be let us assume like that one of the transistor is in off condition, another one goes to on condition. That is the first thing and the second thing is IB2 on. IB2 on nothing but this one. So the IB2 on is equal to 1.5 into IB minimum. And IB minimum, the formula for this IB minimum is equal to IC sat by HFE. Obviously they give the IC saturation and HFE. And the next assumption will be the collector resistor RC1 is equal to the RC2. So the third assumption will be RC1 is equal to RC2 and which is equal to RC. Just we have to find the resistor value. So then we get the value. And the next one will be this R1 is equal to R2. So that is R1 is fourth assumption, that is R1 is equal to R2 which is equal to R dash. And this current, this I2 dash current will be ignored. As we know that here the current splitting is like this. I2 up to this I2, here it can be splitted like this I2 dash and IC2. So after that it can be splitted like this, in this form it goes to I3. Here also I1, I1 dash and IC1 like this. So these are the design assumptions of this monostable multivibrator. First we have to find the resistor value. So which resistor we have to find? First we have to find the RC2. So that is where it is to find RC2. So usually RC2 is connected in between these two. That is RC2 is in between this VCC and VD by which current here it can be flow, that is I2 current. So that is a VCC minus VD by I2. As we know that I2 is equal to IC2 plus I2 dash. So we neglect this I2 dash current, simply I2 becomes IC2. And what is the VD? VD nothing but VCE saturation. RC2 will be VCC minus VCE sat by IC2. Simply this is the RC2 value. It can be like this. So as we know that RC1 is equal to RC2. So that's why RC2 is equal to VCC minus VCE sat by IC2. In case if they give the neglect the junction voltages, it will be VCC by IC2. So that is the finding of RC. And next we have to find the resistor R. So that is the finding of resistor R. simply the R will be, this R will be in between this and the, so that's why VCC minus VB by the current flowing will be IR2, that is resistor. So just I am indicating with the IR2, and here that will be, so sorry, IB2, this current flowing from this current, that is IB2. And as we know that VB is equal to VB is at, why? Because transistor Q2 is non-condition. So that is VCC minus VB is at by IB2. As we know that IB2 on, that is 1.5 into IB minimum. From that we get the 1.5 IB minimum, nothing but IC sat by HFE. From this we have to get that simply R will be VCC minus VB is sat by 1.5 into IB minimum, and IB minimum is equal to IC sat by HFE. Just substitute this value and then we get the IB minimum. After that we get the resistor value. So up to this we find these resistors, and this resistor are resistor. Then we have to find the capacitor value. To finding of capacitor C, to find capacitor C, as we know that the time period T is equal to 0.693 RC. From this they give the time period and we get the resistor value obviously in the previous one. So after that we get the capacitor value. After that we have to find this VBB voltage and R1 and R2. So just find the VBB voltage. What is the VBB voltage? VBB voltage is nothing but biasing voltage. How we have to find this biasing voltage? And so this I2 dash current is flowing through this, that is I3. Simply we have to say that that is I2 dash to find VBB. Designing nothing but we have to find these things also. I2 dash is equal to I3. Simply where it starts I2 dash, it starts at the VD position, that is I3 is equal to, it starts at VD position, ends at the VBB by resistor values will be, what's the resistors here? R1 plus R2, that is R1 plus R2. As we know that R1 and R2 will be treated as R and R dash, that is 2R1, we have to say that R is equal to, R1 is equal to R2, that is I3 is equal to VD plus VBB by 2R1. So VA, what is the voltage of VA here? VA is equal to, this VA voltage is given to this VD minus I2 dash into R1. That is VA is equal to VD minus I2 dash into R1. Simply substitute this I2 dash value here, that is VD minus I2 dash nothing but VD plus VBB by 2R1 into R1. So R1 will be cancelled, and what is the VA? Simply the VA will be VD minus of VD plus VBB by 2. Then what is the equation here? Simply VA becomes 2VD minus VD plus VBB. That is VD plus VBB. The VA voltage nothing but VD plus VBB. So this 2 will be goes to this one, that is 2VA is equal to VD plus VBB, and we know that VBB is equal to what happens? 2VA minus VD, and this is the finding of VBB voltage. So just we have to check the condition how to find this VBB. So in the next class we discuss about what is how to find the resistor R1 and R2, and one more problem regarding this concept we discuss in the next class. Thank you.